So, we're going to be talking about power series. This is section 11.8 of Simon's. So, what is the point of this? So we have been learning about sequences, and sequences allowed us to discuss series, allowed us to add this infinite collection of terms. The real power of this is that we can define something called a power series, which is this. So we take some collection of numbers, ck, and we form this expression. Okay. If this was just a finite collection, if it was just a finite collection of numbers C1 up to Cp, this would just be a polynomial. But it's not. So C1, C2, whoops, C0, C1, C2 are an infinite collection of numbers. And since we have this notion of series now, for any fixed x, we can discuss whether or not this expression, this infinite sum, actually makes sense. Okay. So if we take an example that we know well, if we consider this series, the sum from k equals 0 to infinity, x to the k, we know it's this. It's just the geometric series. Now we can turn this around. We can say, okay, if we take this function 1 over 1 minus x, this thing can be represented in this way, so long as we have the absolute value of x is less than 1. Okay? And you might be thinking, what's the point of that? Well, that's incredibly powerful, because if we had, instead of a series, just a polynomial, then polynomials are things that we can handle extremely well. We can differentiate them, we can integrate them, we can do anything that we want to them. They are some of the nicest, most easily controlled, calculated functions around. A series, a power series, is morally just as good as a finite sum whenever it converges. So this expression right here is, for all purposes of calculation, of differentiation, integration, as we'll later see, it's just as good as a polynomial. So if you can find a way to represent your function as an infinite series, some expression like this for some particular choices of ck, then you can do all these things very easily. So in Calc 2, we've spent quite a bit of time learning all these very delicate methods of integration by parts, U sub, trig substitution, lots of different tools to integrate. If we just had to integrate polynomials, then it's trivial, right? And if indeed we could always represent functions as just power series, and you believe me that power series are just as nice as polynomials, then all those methods get thrown away. So, a brief glimpse into the future, what we're going to learn is that there's a wide class of functions that we actually can represent like this. And we can do things like integrate, like differentiate, just by dealing with the power series instead of dealing with the function itself. So this representation is incredibly powerful. That's the point of this. That's the big payoff. So it might seem like a completely disjoint jump when we talk about integration, differentiation, and we do all these integration techniques, and then suddenly we stop and we start talking about sequences and series. Well, this is where it all connects. We're now going to have this ability to represent functions with a power series and do many things that were otherwise inaccessible. We're going to be able to integrate functions that we couldn't integrate otherwise because there's going to be a way to represent them with a power series. That's the point of this stuff. And this section is a kind of just a warm-up as to what a power series is and when it makes sense. Okay? All right, so let's start with a simple example. This is example 1. Suppose we have this particular power series, the sum from k equals 0 to infinity n factorial x to the n. And what we want to know is, when is this thing making sense? In other words, for what x can we actually have a meaningful expression here? And what does that mean? Well, this expression only makes sense, is only meaningful if it's actually converging, right? So when does this thing converge? Because what we've learned about in our sections we've discovered on series is that, as a brief aside, that series have literally no meaning unless they converge, right? So, classic example is this thing, the sum k equals 0 to infinity minus 1 to the k. We can write it down, but this literally has no meaning. This is not any quantity. It's not infinity, it's not minus infinity, it's not 1, it's not 0. It's literally nothing. It's a meaningless expression. The only meaning we can make out of this infinite sum is to talk about it as the limit of the partial sums. So we spent quite a lot of time discussing that, getting used to that concept. Now we use it for these kind of questions. So if you pick some x, so x is chosen, and you consider this expression, now this is just a series, right? So whatever your x is, it could be whatever. It could be 5, it could be 0.3. You have your x, and then you put it in this expression, and now you just are considering a series. And the question is, when will it converge? And now we just treat it like any other question about when a series will converge. We'll use one of our methods. And the most powerful, the most useful method is the ratio test. So, solution. If we use the ratio test, then we let an be n factorial x to the n. Then what do we have? We take the absolute value, an plus 1, over an. What are we going to have? We're going to have n plus 1 factorial over n factorial just mod x, right? And what's that going to be? That's just going to be n plus 1 mod x. And in order for this thing to converge by the ratio test, we need that the limit, as n goes to infinity, of an plus 1 over an to be less than 1. So that's equivalent to having that the limit, as n goes to infinity, of n plus 1 of mod x. And since x is chosen, it's just some constant. We can take it out of the limit. So the limit is as n goes to infinity, n plus 1, to be less than 1. But this limit is just infinity, which is only true if x equals 0, right? If x was any other non-zero number, then this limit would have to be infinity. It couldn't be less than 1. This cannot converge by the ratio test. So what this means is that this expression is only meaningful when x is 0. If x is non-zero, this is a meaningless expression. So this is not a particularly interesting power series. Okay? So star is only converging only converges if x equals 0, otherwise it doesn't. All right, so let me just make sure I complete this. Has no meaning. So that's our first example, not a particularly interesting example of a power series, but let's consider some more. Change pen color just for fun. What about this thing? Example 2. So, for what values of x does this series, the sum from k equals 0, in this case 1, to infinity x minus 3 to the k over k converge? Okay. Let's check it out. So there's a slight difference here. This time, this series is not a series of the form x to the k. It's x to the x minus 3 to the k, which means that the series is centered around the number 3. It's morally exactly the same thing. Just think of 3 as being 0. Everything's going to work out in the same way. We're going to use the ratio test because, just as before, if we just think of x as being chosen, once x is chosen, this is just an infinite collection of numbers, a sequence. We're just going to add it up with a series, and we're going to see if the series converges, and we use the ratio test. So let's do it. So solution. Let's write the coefficients just to make sure we know what we're doing. This is what we have, right? So then we have ak plus 1 over k. What will that be? That will be x minus 3 k over k plus 1. Okay, so what would the limit be? The limit as k goes to infinity of ak plus 1 over ak. We can take out the x minus 3 since it doesn't depend on k, and it's just going to be the limit as k goes to infinity of k over k plus 1, which is just mod x minus 3, right? Because you're all happy that k over k plus 1 is just going to tend to 1. So we need this to be less than 1. So let me just write it like this. This is less than 1. Well, when is that the case? Well, it's the case when x, let's draw the picture, x is something between 2 and 4, right? So here is 3, here is 4, and here is 2. Because if we unwrap this, and what does it mean? It means minus 1 is less than x minus 3. Less than 1, that's the meaning of absolute value of x minus 3 is less than 1. Let's add 3 to both sides. So that's equivalent to 2 is less than x is less than 4. Okay, cool. So by the ratio test, this thing will definitely converge for every single x strictly between 2 and 4. Right? But the question is, for what values of x does this converge? So we know also by the ratio test that if this limit is strictly bigger than 1, which is equivalent to mod x minus 3 being bigger than 1, so let me write that down. So if mod x minus 3 is bigger than 1, then does not converge. Okay, clearly, because if these terms, if the limit of these terms is bigger than 1, then each term is getting bigger than the next one, so obviously they're not going to converge. They fail to satisfy their divergence test. So that seems to be close to an answer, but it isn't quite. So what do we know? We know that we're all good in this region between 2 and 4, strictly between 2 and 4. We know we definitely don't have convergence if we're less than 2 and bigger than 4, but we don't know about these numbers 2 and 4. And that's one of the key things you have to learn about this, that when it says for what values of x does the series converge, it really means what values of x, not just being able to answer it pretty much completely, but really completely. So we have to check individually these two other points, the so-called endpoints. And we just plug them in. So we just plug in x is 2 and x is 4, and we see what we get. So if we do this, if x equals 2, what happens to our series? Then we just get the sum from k equals 1 to infinity of minus 1 to the k over k, which converges because it's an alternating series. These terms are going down to 0. They're monotonically decreasing, so converges. Good. What about if x equals 4? Well, put x equals 4 into this. Then we're going to get this sum, the sum k equals 1 to infinity 1 over k, and that diverges, as we well know, just by the integral test. The integral of 1 over x diverges. So therefore, we can finally answer this question. This series, call this thing star converges on this half open interval. So it'd be like this. Okay? Otherwise diverges. Cool. So that is our second example. And that's the Bessel function, example 3. And this looks like this, so don't be put off by the name Bessel function. Bessel function is it's a function that you will learn about if you do a course called Fourier Analysis and Partial Differential Equations, which is a course we offer at UC, and I strongly recommend this course. This is very lovely mathematics, and it's mathematics that extremely applicable. It's in everyday life. It's in some sense one of the natural outgrowths of calculus. So if you're an engineer, then this is definitely stuff to know about. And it's a course I've taught, and sometimes we'll teach again in the future, I imagine. So, this is our guy. Let us try and figure out when this thing converges. All right, so same job as always. Let's call this thing star to save time. And let me put the solution. Let's start over here. Solution, so we're going to let an be minus 1 to the n over, this is the same as 4n and factorial squared. Yeah? And then same thing as always, an plus 1 over an absolute value. We're going to set up the ratio test. What are we going to get? We are going to get x to the 2n plus 2 absolute value over mod x to the just 2n. And what about the rest of the stuff? The minus 1 we don't care about. Here we're going to get 4n and factorial squared. Here we're going to get 4n plus 1. And then n plus 1 factorial squared. And then we see a bunch of simplifications. So what we're going to have? We're going to have just mod x squared. This is going to be over 4. And then we're just going to have, so we can put this n factorial over n plus 1 factorial all squared. We know that n plus 1 factorial is just n plus 1 times n factorial. So then this thing here will just be n plus 1 squared like this, right? So what's the limit of that? Well, this thing it's got to be 0 no matter what. Again, the x doesn't notice the n plus 1. Just pull it out from the limit, and then the limit of 1 over 4 n plus 1 squared is always going to be 0. So this thing is just 0, right? No matter what choice of x. Yeah? So this is always less than 1. So a series always converges. So we've had a series that only converges for the point where the series is centered around. In that case, it was 0. We've had a series that will converge on some interval around the point. Again, the point was where the series is centered on. In the second case, it was 3. And now we have a series where it doesn't matter what x you take, it's always going to converge. It's always going to converge. So we see quite different behavior. This thing, think of as a function defined in terms of x, and it's defined for every single value of x. The previous example, it only made sense, it was only defined from x between 2 and 3, where 2 was 2 and 4, where 2 was included. And the first example only made sense at x equals 0. So we have a general result, which is quite key. Let me change color. So this is the general result theorem. Given a power series. There are three possibilities. Possibilities. Okay. Apologies for misspellings. First, actually, this is not the series. I want to write the series in more general form. So x minus a to the k. So the first possibility, series only converges for x equals a. The second possibility, series converges for all x. And the third possibility is there exists an R such that the series converges when we are inside this interval, and it diverges if we either have x bigger than a plus r or x less than a minus r. Okay? And that's the three behaviors we've seen. And this R is called the radius of convergence. So let me put a little picture in right here. So if this is A, then this is A plus R, and this here is A minus R. And then everything which is strictly between these numbers, it will converge. If we are strictly outside, it will not. It will not converge. And it's called the radius of convergence because you can think of this as being like a ball on the line. A ball on the line would just be an interval, and its radius is r. Okay? And it's a number. And further, if you have this in mind, then you can think of the first possibility as being like when r is 0. That's like when you have an interval of 0 radius around the number a. And you can think about the second possibility as when r is equal to infinity. That's when you have an interval of an infinite radius around a. And the third possibility is when the radius is some number which is neither 0 or infinity, it's some finite number. Cool. Well, actually, no. Let's make a table. So, let's create a table like this. Let's put the series here. Let us put the radius of convergence, which I'm going to abbreviate to R of C. And let's see what we have. So, what was the first example? It was this. Sum k is equal to 0 to infinity, k factorial, x to the k. The radius of convergence was 0. I'm going to fill out this third box in a second. What was the next example? It was a sum from k is equal to 1 to infinity. It was x minus 3 to the k over k. And what was the radius of convergence? Well, we found it converged so long as the absolute value of x minus 3 was less than 1, right? So this is the picture. our theorem says that there is some a and previously when we did this guy, we had that a was equal to 3, right? And then this was 4, and this was 2, and then we would converge if x minus 3 is less than 1, so the radius of convergence is 1. Yeah? The radius of convergence is 1, and the third example was this Bessel function. K equals 0, minus 1 to the k, x to the 2k over, let's write it like this, k factorial squared, right? And then we found this thing always converge, so we think of the radius of convergence as being infinity. But there's another concept, and that's the interval of convergence. So let's put it over here. Definition. Interval of convergence. And that's the set of points on which the series actually does converge. The complete set of points on which it actually does converge. Right? So let's abbreviate this to I of C. And then we have a different story. So the set of points where this thing actually converged was just 0. So the interval of convergence is just a single point 0. That's an interval of 0 length. Yeah? In this case, we found it would converge if we had this interval 2 to 4, like this, where we include 2 and we don't include 4. That's the interval of convergence. And in this case, it's everything. It's the entire real line. So it's minus infinity to infinity. Okay? Now, key point. The interval of convergence is a set of points. The radius of convergence is a number. Okay? These are different things. They're obviously quite related, but they are different things. So a common mistake is to face some exam question where it asks for the radius of convergence, or more commonly, the interval of convergence, and the student will give you the radius of convergence. That's not enough. Finding the radius of convergence is just 2/3 of the job for this particular example. We had to check the endpoints to find the interval of convergence. All right. Let's do another example. Example 4. Find the R of C, radius of convergence of this particular series. The sum k equals 0 to infinity of minus 3 to the k, x to the k over square root of k plus 1. This will be our last example. Okay, so same procedure. We have the ratio tests. So we're going to let ak be minus 3 to the k, x to the k over square root of k plus 1. Then we're going to have absolute value a plus 1 over ak. What do we get? We are just going to get 3 mod x, and then we're going to have square root of k plus 1 over square root of k plus 2. Okay, which we can write as 3 mod x square root of k plus 1 over k plus 2. If we consider the limit of this thing, again, the x is not important, the limit, just pull it out. And then we have the limit of this. Okay, if you just focus on the thing inside the brackets, the limit as k goes to infinity of this is clearly 1, right? You can just factor k from the top and the bottom. And then the square root function is a continuous function. So we just have a sequence tending to a limit, and then we're applying a continuous function, right? And the square root of 1 is just 1. So this thing itself is just tending to 1. This should be reasonably natural to you. So if it's not, as I say all the time in class, we draw pictures. Or as I say all the time in class, calculus is pictures. So this is the square root function, right? This thing in the brackets is getting closer and closer to just being 1, right? So when we apply the square root function to something which is very, very close to 1, then we're going to be getting something up here which is very close to 1. Yeah? This is what I want you to do. I want you to translate this stuff into pictures all the time. And if you don't have it in your head as what this looks like, then draw it. Then draw the stuff, and you'll very quickly find you'll look at this and have a picture in your head, and then you'll be comfortable, you'll be clear about what's happening here. That's one of the main things you need to learn at this course, to take this stuff away from the symbols, switch off your memorization abilities, and read what this says in terms of the pictures, and then understand what's going to happen from the pictures. Okay, so this thing just tends to 1. So all we have here is 3 mod x, and we need this to be less than 1. Okay, and that only happens if mod x is less than 1 over 3. So the radius of convergence is 1 over 3. Okay, and that's it, because they did ask just for the radius of convergence, right? If we were going to find the interval of convergence, then what would we do? Well, this series is centered around 0, right? And we know it's definitely going to converge if we are strictly between 1 over 3 and minus 1 over 3. But to actually find the interval convergence, we need to check these endpoints, 1 over 3 and minus 1 over 3. Simply put them inside here and see whether or not they converge. Okay. And what would you think? Well, if we put just 1 over 3, then we're going to get a nice alternating series with decreasing terms. So we will converge here at this point. So this guy will be okay. If we put minus 1 over 3, then these minuses will cancel out, and we'll just have the series 1 over square root of k plus 1, which won't converge. So we won't have it here. So actually the interval convergence, not that it's asked for, but just for completeness, I of c is what? It's going to be minus 1 over 3, not including 1 over 3, but 1 over 3. Yeah? Okay, that's enough for this.